So talking about measurement of partial discharges, we need to remember that there are certain measurement issues related to electrical measurement of partial discharges, which rather complicates matters so that things become pretty difficult in actual in practical terms. So let us look at what are these measurement issues. The first thing is the noise signal to noise ratio tends to be very low. So there is a lot of external interference even under lab conditions, and under field conditions this can be quite unviable. So what we first and foremost need to do is external interference needs to be minimized through use of inline filters. The other problem is that we cannot guarantee that when partial discharge happens, partial discharge will happen at only a single location. So what we are talking, when we talk about the characteristic signature of a particular kind of discharge, this relates only to when we have a single discharge. If you have multiple discharging sites, the signals from the various sites will superimpose on each other and we will not be able to obtain a particular characteristic signal. So therefore, when there are a potentially large number and different types of discharging sites are present, then the characteristic patterns which are associated with the specific discharge site conditions are swamped out. As we have seen before, that for a particular geometric pattern of the void, we have, for example, for rectangular voids, we have a particular pattern. For elongated void, we have a particular pattern. Now, if you have all these different kinds of voids together, discharging together, then it is very difficult to elicit any one pattern from that, and therefore we would have a lot of data. In fact, that is the problem with PD measurement. Right now we do have a lot of measurement techniques at our disposal, but what we do not have is the means to properly analyze these data to get meaningful information out of the data. And so one of the issues that causes this is, of course, external interference. The second thing is when you have the characteristic patterns swamped out by a large number of sites, discharges, and different kinds of discharges happening together. So the problem is that the information that is obtained is never linear, but even then, we cannot really say that PD analysis is meaningless, because even despite all these problems, we do have some information and we can use this information to assess the insulation integrity. This assessment may not be very straightforward, may not be very accurate yet, but already we have a lot of means at our disposal, which makes it meaningful for us to continue with the process. So what is the basic methodology that is adopted in PD measurements? We measure magnitude and repetition rate. As I said, what picocoulombs, what is the magnitude of the PD that is happening? Because bigger PDs, more charge involved, is definitely likely to be more dangerous. Larger magnitudes would mean that there are either larger sites or maybe there are more sites. So discharges from many sites superimposing on each other and giving you a very large signal. Then we need to know the phase. As I say, the location of the discharge on the power cycle waveform gives us important information about the PD site. Relative magnitude of discharges on the positive and negative half cycle. So where do you see the discharges? You see the discharges on the positive half cycle as well as the negative half cycle. Are they similar? The magnitudes of the pulses in the positive half cycle and the magnitude of the pulses in the negative cycle, are they similar? Very often they are not. And this will answer many questions. For example, this will tell us whether the site, what is the location of the site? Is the site encompassed by insulation on all sides? In which case you would have a void somewhere deep inside the insulation, somewhere in the volume. But let's say you have a characteristic signature which is characteristic of an insulation metal contact. In that case, you would probably be able to guess where such delamination is likely to occur and you can take action. It may also be metallic contacts. So for example, when we perform PD measurements in the laboratory, whenever we set up the experiment, the first time we energize the circuit, one thing inevitably happens, and that is we see some characteristic signature. And I will show you what kind of signature I'm talking about a little later. And when we see that signature, we immediately know that we are not, just from experience, we immediately know that we are not measuring a PD inside a void. What we are measuring is a sharp contact in, giving out corona in the air. So where basically there must be some sharp protrusion or some loose contact somewhere, and we need to put that right before we can make any meaningful measurements. Variation with increasing voltage. Increase the voltage. What happens to the PD? Does it increase? Let's say the PD magnitude does not increase, which means that we are dealing with cavity dimensions of we are dealing with cavities of fixed dimensions. So they are all already discharging, and you increase the voltage, nothing really happens. They might, of course, discharge faster, but it's not as if you will have more discharges happening. But on the other hand, if you see that when you increase the voltage, the number of discharges increases, that means there must be many sites, and the smaller voids were discharging with at a smaller voltage. Now, when you increase the voltage, then at that point of time, the bigger voids also begin to discharge. So if you see an increase in the magnitude or increase in the number of pulses with increase in voltage, this will give you an idea about what kind of discharges are taking place, whether discharges are taking place in multiple sites, whether these multiple voids are of the same fixed dimension or they have different dimensions, etc., etc. So what we are trying to do is we are trying to characterize the discharge in all ways possible. Once we have done that, what we need to do is we need to create lookup tables pertaining to specific conditions. So we perform a very large number of experiments where we introduce known discharges, and we characterize the signature corresponding to these discharges. Let's say corona in air, corona in a metal dielectric void, and so on and so forth. Intentionally introduce these or simulate these discharges, take the PD pattern, create a lookup table which pertains to the specific conditions. If condition A, this is the PD pattern. If condition B, this is the PD pattern. And when you do this, that is when you have to remember, that is where you have to exercise your judgment to figure out what are the likely cases that might happen in the field. Reproduce all those cases, simulate all those cases, prepare the lookup tables. And of course, when you do this, your engineering and scientific judgment comes only with understanding of the physical process. If you know what is likely to happen and in what process it is likely to happen, only then you will be able to elicit that information and put it in the database. As I said, you have to analyze the PT pattern for change in parameter values. So voltage increases, what happens? If you look at the phase, what happens? If you look at the positive negative polarity, what happens? All these different parametric changes have to be monitored. You might also want to do a pulse sequence analysis. What I mean by pulse sequence analysis is, what is the nature of the PD? To give you an example, let's say you see a lot of PD activity for a large number of cycles, very large PD magnitude, 5QN patterns, very busy 5QN patterns, and then suddenly you see that nothing is happening. There is a very long quiet period or quiescent period. And then again after some time, let's say after 2 hours, you again see brisk PD activity. This burst of PD activity, if you see that, you are likely to suspect the presence of treeing, because we already know treeing is characterized by bursts of PT activity followed by relatively quiet period. Of course, there is a reason behind this, but I'm not going to discuss this. You can think about it. What can cause this kind of activity when treeing happens? So essentially, all these things have to be foreseen, and you have to create a lookup table. And once you have the lookup table in the field, you get a PD pattern, try to use the lookup table to correlate what you see with what you know, and try to figure out what could be the nature of the problem. And then you would have to maybe run more tests to ascertain whether your suspicion or hypothesis is correct. Now, one of the most important things in PD measurement is calibration. If you remember, we had already mentioned, we have spent quite some time on understanding that what we measure as a PD pulse magnitude in picocoulombs is certainly not the charge that is involved in the discharge, but it is the apparent charge which is defined as the quantity of charge which, when injected between the across the test specimen, across the terminals, would register the same PD pulse magnitude in the measuring oscilloscope as the discharge that is happening at the discharge site. And especially because of that reason, and also because all measurements mostly deal with, in most measurements, you have to have calibration. Calibration is of utmost importance in PD measurements. A PD pulse is an impulse event. So what is the frequency component of a PD pulse? It's in a nanosecond duration, which means that it will have a whole plethora of frequencies. There will be infinite number of frequencies, from low frequencies to high frequencies. All frequencies will be present. Now, it depends upon the bandwidth of your measuring equipment whether you will detect energy. Whichever bandwidth you use, you will detect some energy. At certain frequencies, you might detect a higher magnitude. At certain frequencies, you might detect a lower magnitude. Naturally, you will try to choose your bandwidth of your measuring equipment in that frequency range where you can have very high magnitudes. So that is one aspect. Calibration has to be done at that same bandwidth so that you know what is the magnitude of a known PD pulse in that frequency range for this particular test setup. So calibration is important for accurate measurement, and therefore we have to have a calibrator. This calibrator will inject a calibration pulse into the experimental setup. What is a calibration pulse? A calibration pulse is a discharge simulation pulse. It's not a real discharge, but we send a pulse with the similar frequency bandwidth. So it's again an impulse. It's a discharge simulation pulse, and we know the magnitude of the discharge. We know the exact shape, we know the exact magnitude. So we know the magnitude of each frequency component that comprises of that calibration pulse. This is now injected into the detector at the point where the real discharge pulse enters the detector. And then what we do is we inject the known pulse and we set the measuring equipment to read that known value. So if you are expecting a PD magnitude in the range of 5 pc, you will inject a pulse of 5 pc across the terminals of the PD detector, and you will measure it in the equipment. You will set the measuring equipment to read 5 pc when this PD detector, when this calibration pulse is injected through your test specimen. So when this PD pulse is injected into your test specimen, the pulse that reaches the oscilloscope may not actually read 5 pc, it will read some value. We know that this value corresponds to a real value of 5 pc because we have injected this pulse. So we will set the oscilloscope to read 5 pc. So when we have a PD, now after we remove the calibration pulse, when the PD actually happens, when if we read in the oscilloscope a magnitude which is half this PD pulse value, we know that it's 2.5 pc. If it is 2 times, we know it's 10 pc. So it's what we are doing is we are actually measuring the real pulse or the actual pulse as a ratio of the, as a multiple of the calibration pulse. Remember, this will depend upon the path followed by the calibration pulse. It will depend upon the experimental setup. So if you change the range of magnitude, you will have to recalibrate the test setup. So if you have calibrated it at 5 pc and then you're going to do measurements where the partial discharge is likely to be 100 pc, you will have to recalibrate with a known calibration pulse somewhere in the range of 100 pc. So we must remember that calibration is very important for accurate measurements. Without that, accurate measurement is impossible. In this, a discharge simulation pulse of known magnitude is injected into the detector at the point where the real discharge pulse enters the detector. The detected magnitude is a function of both the injected pulse and the bandwidth of the detector. What are the PD parameters that we are generally interested in? We are interested in the discharge energy because that is what is going to cause harm. Remember, PD is a degradation mechanism in itself. So the discharge energy content is important. So the discharge energy P is measured as Q into V. The discharge inception voltage. When you apply a particular voltage across the test specimen, initially you will not see any PD pulses. Now, if you slowly raise the voltage, at some point you will see the first PD pulse. Initially, this PD pulse will come and go, we are not bothered. The voltage, the minimum voltage at which a single PD pulse becomes steady, that is the voltage which is considered to be the PD inception voltage. Now, when you increase the voltage further, it is not necessarily that you will see an increase in magnitude. Remember our discussion about the pulsative nature of PD and how we showed that the breakdown voltage of the void, the ratio of the breakdown voltage of the void to the voltage that is applied across the void determines the number of pulses per cycle. And therefore, this is exactly what will happen. Once you see a steady pulse, you have the PD inception voltage. Now, if you increase the voltage further, you do not see a corresponding increase in the magnitude of the discharge. What you see is an increase in the number of pulses per cycle. And then after you have seen an increase in the number of pulses per cycle, after that again when you increase further, you will see an increase in magnitude where either you have, if it's air, you have larger volume of air discharging, or if it is voids inside a encapsulated in a solid, larger voids now begin to discharge. So there are many different kinds of things that might be happening. So this is a discharge inception voltage is important. We also measure what is the discharge extinction voltage. So you have started to have a single pulse, you've increased it further, you have very large number of pulses, some of the pulses are of high magnitude. Now you start decreasing the voltage. And at some point, the PD will vanish. The voltage at which no PD is sustained is called the PD extinction voltage. Now the question is, if you know the PD inception voltage, why would you want to measure the PD extinction voltage separately? You would probably expect them to be equal, but that is not the case. You will find that in most cases, the PD extinction voltage is lower than the PD inception voltage. So you need more energy to start the PD. But once you have got the PD going, once the discharge is happening, the discharge can be sustained at lower voltages than the PD inception voltage. So therefore, there is a lot of space charge, and even at voltages less than the discharge inception voltage, PDs can be sustained. So generally, the PD extinction voltage is less than the PD inception voltage, and therefore we would need to measure both these quantities. Apart from that, there are some other derived quantities that we measure. The discharge current, I, which is summation Qy by T. The discharge power, D is equal to summation Qy square by T, mod Qy square. Discharge intensity, the total number of discharges N in time T, because that will give you how much degradation. Quadratic rate is P equal to summation Qy Vi by T. So these are derived quantities. As you can understand, in all these cases, what we are trying to do is we are trying to measure the amount of degradation that a particular discharge can cause. Now, if you look at the calibration strategy does not always work for generators, motors, transformers, where you have complicated geometries, you have materials which do not allow the passage of currents. There will be many complicated things happening. One of the things that can happen is what is called dispersion, in the sense that you have a calibration pulse, the calibration pulse remains constant, but the PD pulse, as it progresses through the various components of a motor or a generator, may become attenuated, so its amplitude reduces because of absorption through the different media, or dispersion happens. What is dispersion? Dispersion means the different. So as I said, the PD pulse has a lot of frequencies, and all these frequency magnitudes together comprise of the PD pulse shape. What will happen is, depending upon the medium, that are present in the generator, these different frequencies will be attenuated at 2 different degrees, and therefore the PD pulse will change its shape, and that will create a problem. You will not know what you're measuring. So the PD pulse may have to propagate tens of meters to reach the detector. The propagation path may be complex, composed of inductive, capacitive, and resistive components, which are distributed in nonlinear fashion. The impedance paths are also dependent on frequencies. Some frequencies may be lost, some frequencies might resonate, and this will all complicate matters. And in these problems cannot all be surpassed by using the calibration strategy. So we will have to do something else for that. So to summarize, the several issues are there. The frequency is important. If you take narrowband detectors, you zero in on certain frequencies that you like for whatever reason, but then if you have a narrowband detector, in certain scenarios, you might end up with a signal which has a very low magnitude, and therefore the pulses of small magnitudes may not be registered at all. But on the other hand, to surpass that, if you use a wideband detector, you're also going to let in a lot of noise. So it is very difficult to figure out how to have a balance between the detector sensitivity and the error. One thing is there, most of the activity takes place near the high voltage terminals, and therefore if you are able to set up your measurements, if you are able to take the measurement output near the high voltage terminal, the likelihood is that the PT pulse will have to travel shorter distances, and therefore it will be attenuated less, there will be less dispersion, you are more likely to get a accurate signal. Number one. Number two, this is of utmost importance. Trend analysis is more important than absolute magnitude. You cannot really say, okay, look, if I have a PD pulse of such and such magnitude, 50 PC, I'm going to shut down my transformer. You cannot come to that kind of quantitative assessment. But what you can do, and what we do in condition monitoring, let's say I buy a new equipment. Right from the outset, I will do a periodical online or offline PD analysis. So I will take the PD, and periodically I will continue to do PD measurements. And when I see a change in the trend, so I'm not really going to look at, okay, I may look at, if I already have some idea about what kind of magnitudes to expect, and I see some values which are very deviating very largely from that, maybe I will look at the magnitudes. But most of the time, what I will actually try to do is, in a healthy system, I will take the PD analysis, I will take the PD pattern and keep it. And over time, I will try to see how that PD trend is changing. And if I see a drastic change in the PD trend, then I definitely know that something is wrong, and then I will take corrective action. So, what kind of trend analysis I will not go into later, but by the time we have discussed, we will have some fair idea about what I'm talking about. But what I'm trying to stress here is, rather than the absolute magnitudes of the PD levels that we are measuring, we are going to look at trend analysis, because that is going to give us a better idea and more more, not a very general idea, but specific to the equipment, information specific to that equipment, we will be able to understand if we concentrate on trend analysis. Noise elimination is very important, because very often in the field, the noise signal to noise ratio will be very poor, and therefore we must use some noise elimination techniques. These can be discrimination circuits, so that what we measure is already rid of the noise, and that can also involve traditional filtering techniques. So right at the outset, what we are registering is the signal. We are eliminating the noise in the first place, at the measurement level, at the hardware level. This is not always possible, especially since often we do not have a priori information about what kind of noise to expect. And in that case, therefore, you will see, if you look up the literature, there is, on the research of partial discharges, there is a large amount of data on signal processing of the data, where we use things like wavelet analysis or neural networks. A lot of work has been done towards eliciting useful information from the measured data. So this brings us to the end of the traditional electrical PD detection circuit. In the next lecture, we will talk about electrical measurement. We'll continue to talk about electrical measurement, but not this particular pulse measurement technique, but other techniques. And we will also talk about non-electrical measurement techniques. And we will see how to put all these various kinds of techniques together, such as to get useful information from PD measurement in the field.